good application for applications. So now, yeah, there is but the equipment what we have functional applications. We could be able to make only simple shapes because having the 3-axis facility, X, Y, and Z. It was not having the another rotational axis or 5-axis disabilities. And there is no, at that point of time, they were not having any closed loop process monitoring, so that we could not understand what sort of multiple or what is the size of that, and whether it is being built properly in the layer by layer could not be monitored. But now the features are there. Data segments are equipped with these features, and limitations again. This was having only 3 and 5, this very minimal, and equipment with higher build size are now available. So these are limited. So these are the most limited features for able to make the components what we have been talking about till now. Then we have then used to develop some other components or critical components. Fusion technology machine that has been used to develop this component. Development of components this component of missile, all type of missile applications. So this is one of the components which have been considered for the development through DMLS technique, which I will talk in detail. So if we see this component, which in the conventional process, it is an assembly of 2 parts. There is an injector and there is an O-ring here. And these parts were complex machined from the cylindrical block using the CNC machines. The part 2, which is the O-ring, it was welded to this one through the electron beam, very costly process of LED. And there were 1, 2, 3 injectors made into the electron. This is a conventional process of 2, 3 the sectional layout here. Part 2 is welded onto the part 1, and this is the fuel injector, and the center one is the fuel injector, and there will be 2 oxidizer injectors, which will be combustion will be taking place. So this is a component which has been considered for development through powder bed fusion technology. So as such, the component cannot be made. There is a requirement for changes in the design. So what changes are required, because there was an internal duct. There was after welding internal duct into which the oxidizer will come and sit before being finally ejected out. So this internal duct was earlier in the conventional manufacturing was of rectangular cross section. So that type of features we can't build in the metal 3D printing process, because there is a requirement to have this type of features. We need to provide the support structure in this structure. But when we provide the support structures in this region, it is not possible to take them out, because we are clubbing these components additive manufacturing. Assembly of 2 parts are being made into one. So there will not be any to remove those support structures. So what we have made is we have adopted a novel design technique where the modification of the design has been carried out. The rectangular cross section has been initially modified to the pyramid-like cross section. This has resulted in a low thickness of material between these regions, as shown here. Then we have changed it to the next to the triangle cross section. So by this, we have elevated the complex machining by taking this component to 3D printing. We have adopted 3D printing, eliminated the complex machining of this component using the CNC machines and eliminated the joining of parts, because the 2 parts have been clubbed into the single assembly. So EBW has been eliminated, and also we have eliminated the requirement of fabrication of 3 injector holes in the 3D printing. These are the primary advantages. These are the value addition of the features that have been made when we are transferring that conventional component into the 3D printing area. So this is the initial design version, 2 parts. It has feature with rectangle cross section, section, 3 injector holes, modified to assembly of 2 parts into one, by which we developed an internal duct region cross section and make it to make.
Sir, Ramesh sir, some voice breakage.
Yeah.
Sir, hello sir. Sir, there is some voice disturbance, sir. Ramesh, voice is breaking, sir.
Is now
No, okay, sir. No, okay. Now, okay, sir. Now it's okay,
maybe
sir.
I'm moving. Yeah.
Now it's okay.
Okay. Then the internal duct region is modified to triangular cross section mainly to avoid the support structures. We need not have to provide any support structure. This is more than 45 degrees. We have more than 45. The design was about 60 degree angle and it was about the support structure in this one. Directly we can realize the internal was not requirement.
Again, it is scattering, sir. Again, the audio is, sir. Again, the voice is getting scattered, sir. It is. Hello, hello, sir.
Yeah.
Hello,
Hello. Yes.
hello, sir. Voice is still lying. Audio is not clear. Audio is not. Now it is okay, sir. Now audio is, there is some kind of lagging in the audio.
Okay. Okay.
Voice is breaking, sir. Hello, hello.
Yes.
Sir. No, sir. We are unable to hear the audio.
Shall I repeat that previous slide?
Voice is, sir. Voice is lagging, sir. Audio is some problem with the audio, sir.
Okay.
Hello, hello.
Yeah.
Is there
okay
an
now?
internet connectivity problem, sir, from your end? Now okay, sir. Now okay. I think there is some internet problem
Yeah.
from your side. It is lagging. It is becoming slow.
Yeah. So is it okay?
Hello?
Shall I continue? Shall I continue?
Continue, sir. Continue.
Continue?
Please continue, sir. Okay, sir. Please continue. Please continue.
Yeah.
Yeah, please.
So I'll just a couple of things I would like to again talk about here. The initial design version has modified into this one where we have eliminated the requirement of where we have structures. Then this component after initial redesign has been taken up. The flexibility again,
Sir, again there is a voice breaking, sir. Voice is breaking, sir. Hello? Hello? Hello, sir. There is no voice.
Hello. You are
Sir,
sharing my
Ramesh, sir, voice is not clear, sir.
Voice is not clear. So
you have any you have any audio set, sir? Hello?
So, audio.
Hello?
Yeah.
You have any mic?
Yeah. Let me see.
Sir, there is some internet, I think, issue. No, okay, there is some internet issue, sir, from your side. It is lagging. Internet is slow.
Lagging. So,
Internet signal may be weak, sir.
Internet is there. Internet is there.
But there is some kind of internet signal weak, I think. Due to there is some bandwidth problem from your side, sir.
For the generic application.
Hello? There is some bandwidth problems. Until now, it is good.
So shall I come out and enter again?
No, sir. No. Actually, internet issue, sir. It is not regarding the connectivity. Hello?
Yeah, your voice is also breaking now. Yeah.
My voice also. You are unable to hear my voice also? Hello? Now I am able to hear. Please continue.
Yes.
Please continue.
Then I will not move from. Yeah. Then this component we have used the facility.
Sir, again voice problem, sir. No, we are unable to hear, sir. We are unable to hear, sir. Hello?
A little.
Otherwise, you again rejoin, sir. Again, you rejoin, sir. Once again.
Yeah. Yes.
Some internet connectivity.
So you had to stop. So you had to stop. I'll stop then.
I think there is an internet issue from your side. Sir, there is some internet issue from your side, sir. Hello.
Internet is there, actually, there is no
We are
problem.
unable to hear. We are unable to see. Sir,
Okay,
otherwise you stop.
I'll,
Sir, 1 minute, sir. You stop your video and switch on only audio, sir. You stop your video, switch on only audio.
yes, yes. Stop, yes.
Sir, hello, sir. Sir, it is not clear, sir.
Let me first check whether it's coming or not. Yeah.
No, no, it is
Is
coming.
it okay now?
Now, okay, sir. Now, okay.
Is it
Please
okay?
continue. Now, okay, sir. Please continue.
Stop there. I'll continue without reading. I don't need
No, it is okay, sir. Now, voice
this
is
is
okay.
the
You can
component.
continue.
Yeah. Yeah. So this is the component what we make the first component using the facility what we have at HAL water bed fusion, that is EOS M400. It is having the in the iron 708 alloy. Major process parameters have been reached that to take the thing off is less than 285 and scan speed layer.
Sir, we are unable to hear, sir. We are unable to hear. Again, there is voice breakage, internet. We are unable to hear, sir.
Voice break. So I will once I will come out of the this one. It is about 285 grams and even your voice is breaking.
There is issue with some internet, sir. Internet issue. Voice. Hello.
Come out of the meeting and join again.
That may not be issue, sir. Internet from your their internet strength is good, sir.
Internet is on. Join again is on. It is showing. Yeah.
Sir, your internet is having good strength, sir. There. Hello.
Sure.
Hello.
Only. It's there. Hello.
Now you can speak, sir. Now you can speak, sir. Now you can speak, please. Hello.
Yeah.
Sir, please,
Hello.
sir. You are able to hear me, sir?
Yeah.
Now it is clear, sir. Now voice is clear, sir.
What about me? Yeah.
Your voice is clear, sir. Please continue.
This is the component again. I'm repeating. Yeah. So I'm repeating once again. This is the component which we have taken up for 3D printing using the powder bed fusion technology with the facility what we have at HAL. So the parameters for the iron 708 what we have freezed is 285 laser power, layer thickness of 40 microns, and hatch width, that means between each the hatch width of 0.11, and again gas flow rate also is at 5 to 6 bars. So again, like to put again this once again the same chart what I have. So it is not going to stop here. The component, once we made the 3D printing of the component, the activity will never end. There are major activities which have to be carried out after 3D printing of the component that are necessary to make it suitable for end-use applications, which involves the complete detailed evaluation of the 3D printed components, which we have carried out for this component in very, very detail, which I'll talk in the subsequent slides. So, especially this component 3D printing, we have made the chemical analysis out of at 6 different locations using the portable XRF spectrometry facility in DMRL. We have full-fledged facilities for any type of microstructural mechanical characterization of in the DMRL. This is the facility what we have, and we have found that the material is very, very homogeneous and elemental composition is in line with the standard AMS 5662 for iron 700 material as shown in this table as all regions. So that has given a very good satisfaction. The material is very, very homogeneous after 3D printing, and then out is that we have done the X-ray 3D tomography of this component using the facility what we have at DRDL. so that to understand it through the CD computer tomography, layer-wise are there. Layer-wise, any porosity is there. So distinctly visible. If we have, and here I will maybe I don't know whether I could able to, Professor Shivaram Krishna, shall I play this video or should not?
You play the video, sir. Play the video. No issues. You play the video, sir. You play, sir. You play the video, sir.
Ah.
It is, if it is important, you can play the.
Open. Okay.
Sir, you can play the, you can play the video, sir.
Stop sharing, no?
Yeah, yes, sir, yes, sir.
Is it coming? This is the computer tomography from one layer. You can see how the each layer section. This is having the result. That layer my class will be having different points different here. So if you can see what sort of pictures we are getting from this one, layer one. Even the interface. You are able to see.
Sir, we are unable to see the video, sir. It is in the still PowerPoint mode only. Hello? Hello? We are able to see. Now you again you restart, sir. Restart. Again, play again, sir.
Yes.
Play again.
Okay.
Sir, please play again.
Yeah. So this is the video. This is the yeah. So to understand, actually this computer tomography of this component has been made to understand layer-wise any defects are there in the different directions. This is one of the video we have taken in one of the direction, which shows, I will play this one. So I play with the mouse. So slowly, yeah, this is the component. Internal features also can be visible. You can see a different sort of feature. So even in this, I'll freeze the image here. Image here. You can see the internal regions. The internal regions are visible, and from this.
Sir, we are unable to hear, sir. Sir, we are unable to hear, sir. Video is okay, sir. Video is now we are able to see the PPT. Now we are able to see
the video first.
Now PPT is okay, sir.
Okay. So I'll come back to PPT.
You can continue.
I'm coming back to PPT now. Freeze this one just after from those video we have I have just freeze some pictures for explanation. In the first picture, this is the front view. We can even see the internal features also have been clearly visible without any falling of the material. From the top also we could able to see, and even from the side also we could able to see. This computer tomography, 3D tomography. From this graphic, see visible the well-formed main channels and also the internal cavity of the component. Component found to be very densely built without any major pores or cracks. That is one second evaluation what we have carried out in this component, and that also has given very good confidence that the 3D printed component has come out very nicely after 3D printing. And then gone with the but taken from that component we need some amount of setting getting from this slide and knowledge signal. Then what we have, the scan tracks are clearly visible in the transverse direction. That means the tracks are visible, and multiple overlaps are also very clearly visible in this longitudinal direction. These are the multiple tracks, layer by layer are formed here. First layer, second layer, third layer, fourth layer. Tracks here we could able to see the top one. That is the top one. That is the multiple formation. Scanning track. This is scan. The scanning like this from the top, like this. It will come to the top. So this is the multiples 1, 2, 3, one upon the other layer will be built in the longitudinal direction. So again, the presence of some grain formations. This is a grain, major grain, and there is sub grains have been formed. We need very fine cellular dendritic structure has been observed. This type of structure, again, the columnar grains are observed in the build direction. The build direction, we have seen the columnar grains, and similar type of structure has also been observed in our experiments of a different material, iron 65 and SS316 in LENS 350. So this is a very generic picture, a generic type of demonstration that we will be taking to have the very fine microstructure. Then what we have is at some regions are there some amount of impurities in porosity. So that is also to be evaluated. What have come up in this one, and what sort of amount of pure porosity is there in this component. For that one, we have gone with the next level of evaluation using the scanning electron microscopy, which is also very advanced equipment available in DMRL. So we have carried out SCF to carry out mainly the homogeneity of fine dendritic structures as well as the impurity particles. We have seen a couple of impurity particles. We want to understand where some the impurities have come out here. So micrographs have revealed very fine cellular dendrites, one order less than. If you see the one order, that will have the 10 times of this type of dendrites, whereas order less than the conventional alloy we have got. That is again very relevant to the 3D printing. This is mainly because of the very high rate of solidification rates, 10 to the power 5 to 10 to the power 6 degrees per second in 3D printing. And again, we have observed some of the heavy elements at the interdendritic region and with high solidification rates, which is not generally witnessed. So we have come out with a different type of things have come in this one. We want to understand what is this one, what sort of impurities are there. Then we have seen certain spherical pores of size ranging from 5 microns to 10 microns due to the entrapped gases. So overall porosity, what we have seen in this semi is that is less than 0.2. That means it is a component has been densely built with a porosity of only 0.2, but there was some problem of some impurities here and there, where we have shown here. Where we have not those impurities, we have gone with the EBA microstructure. So this technique has been employed to analyze the gray and dark particles. You can see in these slides. First particle identified as alumina and silica. Is not having neither alumina.
Again, voice
we were puzzled as why. Yeah.
Hello, sir. Still voice. Again, voice is breaking, sir. Hello.
So why
hello. Sir, you have any microphone, yeah, sir? You have any?
Wait for a minute.
You have any headphone, sir? Sir, do you have any headphone? Please put the headphone, sir.
No. No,
actually, you have any headphone?
Headset itself is very good. I checked the other one. It's very good.
No, you have any headset, sir? Audio headset? You have any earphone? You have? Hello. You have any earphone, sir? You have any earphone, sir? Hello. Do you have any earphone, sir?
Audio.
Hello.
Hello. Hello. Hello. Hello. Hello.
Sir. Hello, sir. Hello.
Yeah.
Hello. You have any?
Yeah.
You have any earphone with you, sir? Here. Hello. Sir, do you have any earphone with you?
Hello. I'm a.
No. Now it is audible, sir. Please continue.
So, yeah. So then again, see what we have seen in the next level of analysis.
Sir, your PPT is not seen, sir. You are not sharing. Now we are able to see. Please continue.
I'm just sharing. Yeah. It's some. Yeah. So then, actually, we have seen.
Sir, press F5, sir. Press F5.
Spot analysis.
Sir, please go to share mode, sir. Share PPT mode. You go, please. It is my presentation mode, sir. PPT you go. Hello.
Okay.
Now it is okay,
Yeah,
sir.
as
Now
I
it is
said,
okay. Now it is shared, sir. Please
So-
continue, sir.
okay. Then we have carried out with the EDA spot analysis. We have seen that the spot will be visible as impurities, majorly they are alumina and silica particles. But iron 709 was not having any alumina, neither alumina nor silica.
Again you came
so
back, sir.
what
Again.
we have concluded is that
Sir, presentation mode, sir. Please put presentation mode for PPT, sir. Now it's okay, sir. Please continue, sir.
so actually if you see
Please continue.
the iron 709 alloy was not having neither alumina nor, is it okay? Nor
Okay, sir. Okay, sir. Please continue.
yeah. Okay.
It is okay,
So
sir. Please
alumina,
continue.
iron 709, yeah. Is not having neither alumina or silica, then what we have concluded from this one is these may have formed due to the contamination of the previous campaign of 3D printing using powders like alumina, 10 silica, 1 mg at HAL. So this information has been passed on to the HAL, and we could able to make some very important when you are transferring from one campaign, when you are transferring from one campaign. And now HAL has taken some additional precautionary steps after having this type of experience, so that the proper flushing of material will be made, and proper flushing will be with additional amount of cleaning aspect is being considered. So in the subsequent, we could be able to avoid this type of contaminant issues. But what I would like to have, we could be, when we are 3D printing, we should not stop at the 3D printing of the component and go for the applications. The component what has been 3D printed has to be initially evaluated in detail, completely, to have a clear understanding whether it has been deposited, any porosity is there, or mechanical properties have been met or not. So such type of requirement is very, very important. Then actually after the so further
Hello?
on this component we want to understand on this component we have strengthening phases have been made. Now,
Hello, sir. Please continue, sir. Sir, please continue, sir.
So we want to understand iron we want to understand what sort of strengthening phenomena is there in this component. Then we were XRD analysis. So conventionally, I think many of you may be aware that 718 is having the gamma double prime, which will come only after the standard heat treatment process. But in the as deposited condition itself it has come again. This has so then the characterization also has been carried out on this one, which is I will do to understand the phases. So phase map revealed gamma double prime, and how much amount of gamma double prime also has been understood. And this sort of microstructure is only due to again rapid melting and 3D printing. Gamma double prime are distributed throughout the matrix, and a volume fraction of about 8% is already there. This is actually what I would like to highlight in this slide is that gamma, the strengthening phase, gamma will come in the conventional process only after heat treatment. But in this 3D printed 709 any additional heat treatment, we could able to get 8% of the strengthening because it could get a very, very fine cellular microstructure. So that is what we have. We could gather the information from this evaluation of XRD and EBSD characterization. Because of the very high rapid qualification is involved in this 3D printing of metals, there is always possibility of having the residual stresses on the component. So we have also made a study on the technique. We in 3 different angles. One is X plus 45 and X plus 90 at 2 different locations. Results also have been shown here. So what we have section and larger section, there is residual standards. Yeah. Hello.
Sir, please continue, sir. Sir, please continue, sir, please.
Then, and yeah. Then using the IMHT hardness of this component also has been checked at two different locations, and we have checked the UTS values, indirect measurement of UTS values of this component, which has been tabulated here. In the forging, what we generally get is about 450 is 1275. In the casting, we get 380 and 910. In 3D printing, as deposited, we are near to casting and near to 40. This 350 to 400 and 1200 is one. So that properties what we will get is near to forging without any additional heat treatment. So this has to be treated to have the proper properties of the component. Yes, that is one level of activity of development of the component has been carried out. This component was the only changes what we have made is we made it suitable for additive manufacturing. We have not still exploited the real advantages of additive manufacturing, which I am going to present in the coming slides on this component itself. So what we have done initially, we have taken the initial design and changed the minimum required to adopt it for the additive manufacturing, then gone with the 3D deposition. But it is not going to stop there. We have to have additional advantages which are feasible only with the 3D printing technique. So what we have made further is that even the flow optimization of the internal channels have been carried out. If you see the internal channels, there is an abrupt change of flow, which we have kept as it is. Initial level. So there is an abrupt change of flow, which always will result in some amount of losses. So what we have converted is that gradual variation of the flow has been made in all the channels, so that even the topology also has been optimized. And again, in the next level, we have also introduced some amount of lattice structures, so that the low stress regions have been avoided to have the lattice, so that the weight will be reduced by this one. So this is from the initial model, first level, and with the lattice and flow optimization, this model has been freezed. And what are the advantages? I'll summarize this advantage what we have gained from this 3D differentiation. This is model what we have made a modified version. Assembly of two parts have been made into one. Region is modified to make it suitable for the additive manufacturing. Then we have gone ahead with the modified version. Assembly of two parts into one. Interduct modified. Flow passage has been optimized. Redesigned for smooth flow of passage without any abrupt changes. Further, the modified version 3 assembly, including these two, redesign for smooth flow and redesign the component for weight reduction through topology optimization by introduction of the lattice structures. So this first version and third version has been taken up for 3D printing, and this is the build layout what we have finalized for taking the component. These are the third version and this is the first version. And one other advantage of 3D printing is that we can have different type of designs in a single deposition of this one. That means different designs we can obtain at the same point of time and be studied in detail. So we have this build layout what we have, and also many number of specimen blanks also have been incorporated, so that we can understand what sort of properties are going to obtain in these three different directions, so that we need not have to go for any distributed testing of the component. Distributed testing the build layout, and next slide I'll show. This is the component along test blanks. What we have got after the 3D printing of this component has taken about 48 hours for us to 3D print this complete build of this one. These are the test blanks. These are the three different components. These are the test three. Design version. You can see this is a after
Sir,
cutting from the
voice is breaking. Sir, some internet
I
issues.
think I have to wait for a couple of minutes.
There's some internet issues there, sir, from your side.
Now?
Some, I think. No, it's okay, sir. Please continue.
Then yes.
Please continue. No, okay, sir. Please continue.
Yes. So this is the build layout what I have mentioned for the three different components. And this is after the build layout what I have single the machine. These are the two. These are the two. These are two planks in 3 different directions at different places to understand what sort of build has been taken place and to understand even the mechanical properties by testing these samples. And after cutting the plate, these are the two topology optimized fuel injectors. These are two views, and now further activities also has been going on these components with the sample extraction, characterization, and testing of these components is going on. So in the second level of development of this component, second level in the 3D printing of 3D printing of fuel injector using the powder bed fusion technology. I have already spoken about functionally graded materials using the lens applications, and also what sort of design of experiments are necessary to optimize the process parameters, and to understand very detailed evaluation is necessary whenever we go for the 3D printing of metals. Also, I will be. So I will summarize the activities which have been carried out. The fuel injector component was studied and made necessary modifications. Assembly of 2 parts have been
made. Sir, can you go back?
Eliminated.
Can you go back to the previous slide, sir?
Is it?
Sir, your slide is not visible, sir. Your slide is not visible.
I'll wait.
Now it is visible, sir. Now it is visible.
Yeah,
sir, it has come, sir. Now you put in the presentation mode, sir. It is in the presentation. Please explain this one, sir. Just one. Now it's okay, sir. Now you explain this one.
Yeah. So actually, the previous slide is okay. Previous slide, the build layout and other things is okay, sir.
Okay. Okay, sir. Okay, sir.
In the as deposited after taking out from the machine, this is how it looks after removal of the powder and other things. These are the two modified design versions. These are the two modified design versions of this component, and this is the modified design version 1. So that I want to say that in the 3D printing, it's possible to have the multiple designs. It's possible to fabricate it at the same point of time, so that you evaluate or assess each design independently without any wastage of time. You can have the parallel evaluation methodology for 3D using the 3D printing technology. And these are the after cutting for the base plate. These are the topology optimized fuel injectors what we have got, and further activity on the sample extraction, characterization, and testing is in progress regarding this component. And so what I'm saying is that these are the various activities what we have carried on fuel injector. Earlier I have mentioned that using the lens technology, we have using the lens fabricated the functionally graded materials of IFI via Z for hypersonic applications, and I also mentioned that detailed evaluation of any 3D printed component, especially the metal 3D printed component, is required to clearly understand whether the component has been deposited completely, fully densely, and whether the component is giving required mechanical properties or not, or any impurities have been found in the component. Only after that only it has to be released, and mechanical property it has to be released of qualification and certification, which I have not touched, but I just told it is necessary to have the component for end-use applications, especially in the aero and what we are working on. So that is a major area. And to summarize here, the fuel injector component was studied and made the necessary modifications to make it suitable. Initially, to make assembly of 2 parts have been made into one. We have eliminated initially the expensive CNC and EBW process, less wastage. Then we have adopted the novel design technique to avoid the support structures. The 3D printing component has been successfully 3D printed using the HF 3D printing facility, and detailed evaluation of this fuel injector has been carried out, like X-ray 3D tomography, XRF testing, detailed optical microscopy, SEM, EBSD, the microscopy, and elastic modules were evaluated. And what we have seen is that there is less wastage of material. Conventional component was earlier manufactured The conventional component was earlier manufactured from a block of 2 kg to have a component of 400 grams, which was resulting in 80% of wastage. Whereas in 3D printing, we were not having any wastage except the support, except some of the additional specifications that are required for the testing have been made. And we have also, after doing the weight optimization, we have obtained the 25% of the weight reduction when compared to the conventional design. So we have successfully demonstrated the feasibility of relation of the component initially. Now we are working with the second level of design, and the evaluation is going on this component. So in this slide, I would like to touch the major challenges of 3D printing. So what are the major challenges? With our experience, we understand the powder production technology for standard alloys and new alloys. Currently, within the country, standard alloys and countries that are required for metal additive manufacture are not available. Majority of the powders are being imported, and they are, because of that, the initial cost of material is very, very high. We have to address the powder production of at least the standard alloys stages, so that the cost of the product will be coming down by using the indigenous powders. Another technological challenge is the process development standardization. It is part and material specific. Every part itself is a new, and every time, of course, material can be there. The process optimization by parametric studies have to be made. The process and machine dependency. If it is a PBF process, it will have a different type of development activity has to be carried out, and if it is powder bed fusion, again it is a different technique. And post-processing treatment, like improving the surface finish. Surface finish, what we get from the component which has been deposited, is to the high level that has to be finished by adopting certain amount of post-deposition by techniques like abrasive flow machining and other techniques. In many of the aero engine components, tipping is also a mandatory requirement which has to be adopted. Then the third challenge is the process modeling of the metal 3D printing in addition of the properties. So we should be able to process the model. Process modeling has to be carried out. What sort of properties we are going to get beforehand itself, instead of waiting for the deposit to be completed and taking the evaluation. This is one of the area one has to look and work in depth, so that a clear understanding in prediction of properties can be made in advance to save the time and also the money. Then another one of the major technological challenge is the qualification and certification methodologies for defense applications. Knowledge is required for more powder material for 3D, is required for, and also for components of aerospace grade. And another technological and currently what all the 3D printing equipment for metal at USA are majorly imported. So and now it is also required to develop and manufacture 3D printing equipment itself, at least in these powder bed fusion and 3D technologies in the initial levels, also can be an area has to work. And also for the polymers, composites is also major requirements will be there for defense, at least for this type of technology. So I would like to conclude my presentation by this slide. So 3D printing, what I would like to say is that 3D printing is advancing at a very, very fast pace in both its UDF and its has many advantages. Properties, what we have found, properties of lens deposited 719, 65, 316 are found to be at par with the experiments what we have carried out with that of the raw materials. It is also, we would like to say that 3D printing technology can produce parts. Only thing is that we have to optimize the process parameters so that we can get the similar strength as that of the process parts have been made by the conventional processes, like so FGM, we have carried out the FGMs and successfully 3D printed using both DED and PBF technologies, including extensive testing evaluation. And also we were able to demonstrate many of the advantages of 3D printing. And I would like to say, worldwide, the firms are making very huge investments in this technology, which indirectly shows that the future potential of this technology, manufacture of parts, mainly for the end use applications. I'm again specifically saying that metal components are mainly for the end use applications. So a lot of advancements are there. Huge investments are going into this area. And if you see in the last 3 or 4 years, Lot many new areas of developments have come in this metal 3D printing. So 3D printing. So final conclusion is 3D printing is a very magnificent and revolutionary technology. The sooner we can integrate into operations, the sooner design and manufacturing capabilities and speed will increase, while production costs will also goes down at the same time. So with this slide, I would like to conclude, and many thanks for all those who have listened me patiently for the last nearly about 1.5 hours. And I will, if questions are there or
Sir, you can switch on your video, sir. No. Sir, you can switch on your video, sir.
yeah.
So I request the participants, if you have any questions, you can ask. There is one participant 3DP 130. I am unmuting you. Please, you put a question in the. I am unmuting you 3DP 130. Can you ask your question, please? Sir, Ramesh Kumar, sir, you can switch on your video, sir.
This slide, switch on me. I just have to click.
You have to click that symbol is there, no, sir. Stop. The video is there, no. Beside mute, you have video.
Yeah.
Beside mute, there is one thing, sir. Video. Stop sharing, sir. Then you can switch on your video.
Stop sharing. Yeah.
Even without stop sharing, also you can switch on your video. Yeah, no, it's not. So, audience, anyone want to interact with the speaker, you can ask questions. So, on 3DP 130, you have any questions, please? You have put a question symbol 3DP 130. Anyone wants to interact or having queries? It is open for discussion. Please, the scientist has come all the way, so has given a very informative lecture in depth on metal 3D printing, complete industrial aspects. So I request audience, you have any doubts, please post your question chat box, or if you raise your hand, I will put you a panelist and you can talk with the presenter, scientist. You can also talk with the presenter. So if you have any questions, you can raise your hand on 3DP 130.
Yes, sir. Yes.
You have any question? Please ask. Please ask. Please go ahead with your question, please.
I have scheduled the class. Kindly post link.
I have posted the link already. All of you have posted the link. Feedback link already posted. I think you are not listening. I already posted the feedback link. Hello, any questions, please? Any questions, please?
When I can find solution for composite.
Hello, you are raised hand on. Please ask your question, please. 3DP 130. You are raising your hand. Please ask your question.
Yes. Yes, sir. Good evening, sir. This is HK Dora from Mokkamja Engineering College. Sir, I have one specific question.
Call me after.
Sir, please proceed. Anmandara, please proceed. Hello. Please proceed, HK Dora. Please proceed.
Yeah, sir. Sir, actually, I query that in the defense applications, sir.
Hello, please proceed. Hello, please proceed. Sir, one question is asked, sir, from Chitambaram K. What is the latest research going on by using metal 3D printing in medical field?
Yeah, lot of advancements also are there. Medical field means that dental, we have lot many, maybe I think you are also aware,
Yeah.
not much of research is going on, and even the applications and to a certain amount of maturity also is there. And the implants, bio implants, joints, majorly about the orthopedic implants, people are working, and that will be one of the area where a lot of advancements are going on.
In fact, tomorrow we have two speakers from doctors who are using this implants, metal implants. One is orthopedic surgeon in the from 11:40 to 1:10. Other person is dental doctor, maxillofacial surgeon, who is also expert in 3D printing in dental application. They are going to talk about complete on biomedical. I hope they will be able to answer exactly what you require. SAR is basically on aerospace and other side. Of course, SAR is in metal 3D printing. But you can get exact solution. Still, Doragar, any question? You raise your hand, you are not speaking. Hello? Hello? The problem. So, any question still coming up? So, it's only one person.
Attendance 81 displayed.
3DP 130. Anyone? Please ask your question, Doragar. Please ask. Your voice is not clear. Hello? 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 Your voice is not clear. Either you can post your question, sir. Another question, sir, from Rupa Tulsi. She says, how can we control porosity?
Yeah, that's what. See, actually, for any, there are three or four major parameters in 3D printing. It is powder feed rate, scan velocity, hatching, and also this power settings. We have to understand at which optimized parameters we are able to get the maximum density products. That is the reason why in the first slide, in one of the slides, I mentioned about the design of experiments. We have to carry out the experiments of making small samples of these products of different sizes and understand what sort of porosity is there at different process parameters of combination of the process parameters, and see what sort of porosity is there. But presently, what all the materials what we are getting from the already established OEMs, we are getting a ready-made that may be applicable only at certain level. Depending in number in other components, there is also need to have a different type of porous structures. Then you have to modify accordingly to that level also. So that's what we have to understand the process parameters. Optimization of the process parameters and standard design of experiments is necessary. Beginning whenever you are working with a new material. For established materials, they are available, but still, if you want to further work on that, it is also possible.
Sir, always our participants are asking one question regularly: how to reduce the residual stresses in a metal 3D printing? How to reduce the residual stresses in metal printing? That was the question asked.
Yeah, how to reduce the residual stresses is majorly actually whenever you deposit the component, there should be a proper heat transfer has to be taken and to the base plate. And that is one thing. There should be a proper heat transfer of the component to the base plate so that there will not be little amount of distortions will be there. Whenever distortion is there, resistances will come up. So if you reduce that one, it is possible to have the proper heat transfer. So build analysis has to be carried out in advance and to clearly understand what sort of heat transfer is taking place. Then only you can
Sir,
reduce
we have to do any
Sir,
kind of heat
intermittent.
treatment, sir? Do we
That is
have to do
later
any
stage,
heat
yes.
treatment at a later stage?
Yeah, that is latter stage. Then what to reduce the resistances is one technique, and to relieve the
Remove the-
resistances is the technique. Relieving is different from the reducing.
Yeah. So we have to do very carefully during the beginning itself to track
Beginning itself, build
temperature
analysis
gradient
is
should
very
be properly maintained. Yeah.
properly maintained.
Okay. So if not any questions from the audience, I hope we'll conclude the session, sir. On behalf of the organizing committee of 3D printing design workshop Atal AACD program and from the Department of Mechanical Engineering and CPDM, I would like to thank our honorable speaker of today's evening session on metal 3D printing, Sri Ramesh Kumar Garu, for your very in-depth and scientific analysis. Especially the first slide itself was very interesting. What you shown to us, that is very interesting, and the other slides are very informative and exhaustive. How metal 3D printing can solve such complex, especially the last figures you have shown, the complex components. I think it's unimaginable to produce within a conventional method. So that will showcase how 3D printing is going to work in future, and also
Yes.
the complex problems, how it can be solved. And you are telling in future it can be used for higher productions also, because as the technology is improving. I hope as a 3D printing expert, I know you will be shortly getting a doctoral degree in 3D printing also, sir. And you are doing a wonderful work. I think you are having excellent facilities, and with all the facilities, I hope you will be giving some more lectures to all of us and enlightening us on how 3D printing can help metal 3D, especially metal 3D printing. I hope you know we also procured SLM with us, selective laser melting machine. So we will also take your guidance and help how to solve those issues, and when we do the work completely on the SLM technology. Thank you very much on behalf of the organizing committee, and welcome you all. And now, sir, thank you very much, sir, from our
Thank
side.
you, Professor Sriram Krishna, for all the efforts you have taken in conducting this program, and wish you all the best for the remaining program successful.
Yeah. Thank you, sir. Our other coordinator, Professor Sriram Venkateswar, also asked to convey his thanks to you. He is the coordinator of this and director of the Center for Product Design and Development.
Yeah.
Thank you very much.
Thank you.
For sparing your valuable time. Thank you, sir.
Thank you.
Thank you, sir.
Thank you all the participants for listening to me.
Yes. Thank you.
So
Sir.
I'm leaving the event then.
Okay, sir. Right. Thank you, sir.
Thank you. Bye bye.
So I thank all the participants for participating for this today's session. I have posted the feedback link. All of you, please fill up the feedback link and submit your assessment to it. And also, I would like to inform all of you, tomorrow's session will be very interesting. The first session will start with the Professor Surya Kumar sir, that is on design for 3D printing. The second two sessions will be taken by Dr. M.V. Reddy from Sunshine Hospitals. He is going to speak on orthopedic application of 3D printing, the challenges. And the next speaker is Dr. Abhinandan. He is going to speak on application of 3D printing in dental and maxillofacial surgeries. So please don't miss those sessions. They are very interesting. And these sessions will help you in doing some biomedical modeling, etc. in the next day. That is, on next day, you are going to have a hands-on practice on biomedical modeling. I'll be posting in your WhatsApp group the procedure how to download the Cura software and a Slicer software, so that you can have hands-on practice on your laptop whenever we do this on Thursday evening session, last session. So thanking you all for joining. I request all of you, please try to first name you enter your unique ID that we are given. Second name you enter your full name. Then please do it. Most of you are following, but some of you are still continuing with the old one. I request all of you, please go ahead with that procedure what I explained to you. And I want to clearly inform here is those who filled up the Google form and also attending this program, and you are seen, and I am having list of all the people who are attending here. It is displayed on the to me as a host. Everyone attendance is there. So only for those people you will be getting the certificates. I am once again reiterating. Simply registering in Atal portal, you will not get certificate until unless we post the attendance. You will not get the certificate. So take it seriously and try to attend the next sessions completely. All of you, I am expecting in full strength. Otherwise, you will be denied the certificate. It's a clear. I am giving you a clear picture what is the rules of AICT. So simply registering for a Atal AICT program and confirm your participation will not get you certificates. You have to attend the programs. You have to listen to the programs and submit whatever is asked. That is the feedback form and as well as the attendance feedback and attendance form and everything. So please follow these rules. And it doesn't matter how many people will give certificate, but who listens actually regularly and comes to listen the program will get the certificate. And you write the examination completes with 80% marks and submit the overall feedback in the Atal portal. This feedback is for individual hour sessions, but you have to finally submit a overall feedback in the Atal program. There is feedback for the participant. You have to submit that. Then only you'll get the certificate. If you do three things: attend regularly, 80% attendance, you should get 60% marks in the end exam, and also you should submit a feedback. Then only you'll get the certificate, right? Thank you very much. I'll post you tomorrow's link to your emails, and please join tomorrow sharply at 9:50. So the speaker will come by 10 o'clock. Please join by 9:50. Thank you. So the feedback and attendance link is already posted in the chat box. Please observe the feedback and is posted already in the chat box. I am again posting the feedback and the attendance link in the chat box. I am posting the feedback and attendance link again in the chat box. So thank you very much. I am stopping this session.